All right, we have two presentations today. Thanks everybody for coming, joining remotely. First is Scott Shea and Cassandra. I'll let him introduce his topic fully, and then I'll go after Scott and discuss, well, possibly multiple topics, but at least Go and MongoDB. So, go ahead.
All right, thank you very much. Some of you know me, you've worked with me here, or maybe even other places. I primarily do Rails work, but recently have been asked to start integrating Cassandra into a project that we have going, and as part of that, I'm pursuing certification. So I was hoping to find out if I had passed my most recent test before this, but have not heard the results yet, one way or the other. So I don't know that I need to go over this slide too much. I think I'm going to bet most of you have heard of them before, that they have come up. One of the things I did like about our training, though, is they talked about specifically with the volume, velocity, and variety. If you can't answer yes to any one of those three, you probably should avoid big data. And part of that is on the idea that, yeah, you can get the volume and the velocity on a regular non-relational database, but the cost is extremely high for the hardware. Whereas with big data systems, they're going with commodity. With the relational data, this just goes over, to why you wouldn't want to necessarily go with relational data. Again, it pretty much comes down to what are you pushing and how are you pushing it around? What speeds do you need? The other thing that we'll go into more later is that Cassandra and others really go for. Do you need to hold up on that?
Just keep going.
Okay. For any of them, they go for the idea that the partitioning is very easy, but they do have to sacrifice some of the things that relational databases do give you them. Distributed across multiple nodes. The largest one that DataStax, who was giving the training, can talk about is 500 nodes. That is with Netflix. They actually have a couple others with 500 node clusters. They have three private customers that have gone up as high as 1,000 nodes. With that, the inside of the databases then themselves, you have to relax some of your requirements. But you can then optimize the data to suit your actual needs, and we'll go into that when I talk about modeling a little bit. Yeah, I think the only one that I'm really sure on is that, besides Cassandra being a column family, is that Mongo is more of a document-based. And then the three that they talk about are the consistency, availability, and partition tolerance. And I think this next slide goes into that a little bit more. Is that with relational database, they're very much focused on giving you consistency and availability. You have to pick two. What the others have gone for more is how do you easily fragment, shard, add resources without disrupting your entire application and production. So with this one, you can kind of see they show, and by the way, I borrowed this straight from DataStax, so I believe this is correct, but if there are any inaccuracies that you know of, please let me know. For Mongo, you see that they go more on the partition consistency leg. Cassandra goes more with partition tolerance and availability. However, what you can do is configuration, especially at the query level, you can move that more to consistency. So if you're dealing with financial data and when you're getting back all your various copies of it and they have to agree, you can say that right in there. If you're, say, taking an upvote on whether or not somebody liked the white album or the number of users in a database that do like the white album, you don't necessarily care that there's yet one more person that likes it as of that second. So later on, you can have an updated level. You can just give me your latest one now. Yeah, Cassandra is freely distributed. They have a fully distributed, I mean, with no single point of failure. There is no master node. The closest I've seen that comes to that is that you have seed nodes that you configure nodes with. So if you bring a new node, you go, here are the ones you talk to find out what the system is. If you give it, 3, 4, 5, something like that, you'll be just fine. You don't want to give it the whole list. You don't want to make it one. But it gives the idea that when it comes on, it can actively work with the system, and in fact, it has to have a seed node to be fully introduced into the system. If it doesn't, then it doesn't matter. It won't connect in and come on board. It is open source. It is a top-level Apache project. Came out of Facebook. They originally had done they combined Google's Big Table and I can't remember what the other one that they did at the time. They released it out from Google. It was funny, a couple of years later, they went back to it thinking, oh, okay, we can use this now. In the meantime, they developed quite an expertise with Hadoop, which was more led them into HBase. So even though Facebook started it, they don't actually actively use Cassandra now. Big customers are Netflix, Intuit, NASA. I can't remember all the lists that they showed us at the time. It does horizontal scaling. You can do vertical scaling as well. If you find your machine is running low on RAM or disk space, you can add those. But the idea being that after you've kind of maxed that out, or even not maxed it out, but gone for cost effectiveness, gone higher, it may be cheaper just to add another machine than it is to, say, go out and buy very expensive RAM or CPU upgrades. Cassandra uses the CQL, Cassandra query language. They actually call it SQL internally, just to confuse us all. You'll find it's very similar to what you're used to with SQL. The one big thing is there are no joins, and we'll get into that later. But they don't allow joining. I'm trying to think some of the other ones that will easily jump out at you. Between isn't supported either. There's an example of creating a table. Should look pretty familiar. They're not kidding when they say denormalize. The idea being that when you structure your data, you may have a table that is cities, and then you'll have cities by state, cities by county, cities by zip code, cities by whatever. Each of those becomes its own table. Because it's RAID optimized, that they felt that that was a way to go about doing that. So you do your joining in your data modeling when you're originally planning it. You realize you're going to need these data points often. So you create tables around that and pull from that table rather than consistently having multiple tables that you do your joins with. It's like, no, we put it all into this one table. We can go there and grab it. Apologize for the size in this, but the data is divided up among the nodes so that each piece of data is given a partition key that is your primary key hashed and laid out so that you can, Cassandra can then store it based on which node has been assigned that hash. The replication factor is how many copies of that data you want. If you want to run fast and loose, you have a replication factor of 1. Most people run with replication factor of 3. Even large clusters only go to 5. Odd numbers are certainly better than even numbers. And anything more than 5, and they find there's too much churning of data being pushed around amongst all the nodes. The partitioner determines which range goes to which node. So if you've got 5 nodes, and say there's just 100 partition keys, there's more than that, but each one would get 20 that they would handle. And then a node has a node token that's simply the highest partition key that node will handle. And so it just compares to say, are you higher than this or not? Well, guess not. It's not your piece of data. We can move on. Partition keys themselves, oops. Sorry, I made a slight typo there. I should have that 2 to the 127th minus 1 value token range, not 2,127 minus 1. Essentially, it's just a large ring of tokens going from positive to negative that get assigned to the data. That's as many records as the Cassandra will hold. Now, you can do more to put more into your system, as far as like you can have almost an entire database in what they call a wide table that you would then access by one partition key, but that is generally it. It's just then assigned out to each of those. And so in a simple configuration like what this shows here, each one of them has a quarter of it. then going forward, if say you have a replication factor of 3, if the initial copy goes on to node 2, then node 3 and node 4 would get a copy as well. And it would just move up around the circle. It never goes down the circle, it always goes up. No specific copy of the data is better than anything else either. They're all equal, with the exception of last write wins. So if you write and you say you want a replication factor of 3, the last one written will be considered the authoritative source. So if it became corrupted and has null values, which is rare, but I guess it could happen, then you would have null values. But whatever was contained in there is the one that actually goes. And that also then works when you update tables as well. They use a murder-3 hashing process. You can do MD5 if you want to. And then it's just distributed around the circle uniformly. Virtual nodes are, and please forgive me on this, it's not a very easy concept. In the previous slide that I was showing you, that presumed that each quadrant had just that entire range. Really what they do is they take slices of ranges and assign them to nodes so that when you bring up a new node into your system, you don't have that new node turning to the ones on its left and the right and going, okay, give me everything I need, come on, force it, and then ultimately what you have then is 2 nodes completely taken out of play while it updates the new node. Instead, the data is all around the entire cluster, so it can pull from multiple areas and distribute that load around. The one downside is that it is not currently available if you have Solar or Hadoop layered on top of that. And please, I've been speeding through. If anybody has any questions, please speak up. The replication factor is assigned when the key space, which is the equivalent of the database, is created. So if you have a database of geographical points, you're assigning all geographical points have a replication factor of whatever you would assign to that. You can then also then assign that across clusters as well, as you see down in the bottom where it says, oh, you're using the strategy of replication across multiple clusters. Then you can divide it up and say, okay, I want a replication factor of 3 in one cluster, but 2 in another. If you do have more than one rack cluster or rack or data center going on, the first one is always placed locally. The second one is also then tried to be placed outside of your local area so that you have that the failure availability if one goes down. The network topology is the one that actually distributes that across the nodes and the racks and the data centers. Simple just simply goes, okay, here's your next one. And that's the one we use in our development center in a small instance. When a write or read comes in, it is given to a coordinator that's chosen by the driver. It's a round-robin process, so it just says, okay, what's the next one up? That coordinator is then the one that does the communication inside of the cluster. It may or may not have the data on it. In fact, on the large clusters, it's likely not going to have to, but what it does is it coordinates the read or the write out to whichever nodes are available. Or in the case if you're going to another cluster, it then taps somebody in that other cluster and goes, okay, you're my coordinator over there, so that I don't have to do multiple calls to that other cluster. If the target node is down for a write at that time, the coordinator then holds it in a hint file that it then passes back out when needed. And then there's the gossip protocol, which I believe I go into more later, is the nodes talk to each other about each other's health as well as what they know. It's like, oh, dear Fred's sick. Oh, he is okay. I won't hand in any data. Consistency level can be, there's a default of 1, but it's configurable by request. And this is where you start tuning your queries based on availability or consistency. You've got dozens of, or about a dozen choices. You can say any node, any response, all responses, 1, 2, 3, a quorum, which for a small network is usually just a majority. For a larger one, it goes a little bit higher than that. Then you can do local quorum. If you want, okay, as long as I've got a quorum for my local cluster, I don't care what the other one does. And then this also works for writes, as even though you have a replication factor of 3, if you say, look, I'm just going to tell you, as soon as the first node has written it, I don't care anymore, that will be considered a success. If you absolutely have to know that write made it and made it to all copies of it, then you can set that to 3. And then a success will only be judged if all of the nodes respond back that, yes, we wrote it. It's a continuum between the immediate consistency and the eventual consistency. The formula is that if your nodes written and nodes read are greater than your replication factor, then you've got immediate consistency. Now, with your nodes written, you never want that more than your replication factor. You don't want to say, I want to write to 3 nodes, but your replication factor is only 1 or 2. In some versions, that will be an outright failure. In others, you'll get an error message back saying, no, we can't do this. You told us at the database level I only need 2 copies of this. I'm not going to write 3. And then you do need to make sure your server clocks are in tune amongst all your nodes, because last write wins, and if one's in a greater time zone, then it's going to win, even if it wasn't the most recent write. Node repair can go through and just make sure that all your replicas of the data match. You can initialize, and you can set that off manually, and you'll do that if you need to bring up a node. But it also can be triggered by writes. There's a percentage chance that it'll sit there and say initialize to node repair, or if your coordinator gets 3 copies back and finds that one of the 3 or 2 doesn't agree, then it can set issue a node repair at that point. The gossip, it just known states and locations of data. It doesn't talk to everybody on the network. It just picks 3 to 5 random ones and says, what do you know, what do you know, what do you know, collects that data, and then those nodes also pass on whoever they've gossiped with recently as well. That's collated and then stored locally so that when it acts as a coordinator, it can pick one. If it has a choice, it'll pick one that's not as busy or just ignore one that's down. And then when you first join, you have to gossip with your seed nodes. They also have the snitch. It is not the golden snitch. It's just a way to inform yourself of the topology and tells you about all the racks and the data center so that you're not stuck waiting to learn, or if you don't have to instruct your Cassandra cluster about its own topology. It can do that for you and then inform the node what's happening with that. And then you can write your own if you really need to. Now, Cassandra is write optimized. It chooses to append. Deletions are handled in a different way. It writes out what's called a tombstone. It later comes along and gets garbage collected and removed from the data file at a later time. It's not done at the time. There is no seeking going on. It just appends a new record. If you're an update, it just appends the partition key in the fields that were updated. When you read, then it has to assemble all of that into one read that was going back. The coordinator does store the copy, like I said, with the hint. The way it works is the first thing that happens is it's just the data is just written to a log on the system. That will get replayed during if it collapses and you have to bring it back up. The data is then stored in a mem table, which is in heap memory. And then after a while, it gets flushed to an SS table, which is, again, another file. And then those SS tables undergo a concept of compaction. So as things get written to it, it becomes more and more fragmented. The compaction brings it back together and slams it in, removes all deletions, and then completes the data into one record as opposed to having it broken up amongst all the most recent updates. Commit logs append only. Yeah, I think I talked about most of this. When you hear what is known as a CQL table, that's a combination of both what's in mem table and what's in SS table. So if there's an update that is in mem table, it will be grabbed out of memory and then combined with whatever was stored on disk. These are the various files. You have your compression, your data, your filters, the index, statistics, the summary, and a table of contents, which I believe they're going to remove because all it does is list these files for that particular one. These will be in a folder with your table name. So like when I said cities earlier, you might find cities on the disk, and then underneath each of these for the cities folder. Read path that returns the most recent record, consistency level, how many nodes have to respond for it to be a good read. And then eager retries is if one node is taking too long, it'll go to another one and say, hey, do you got it? Okay. The coordinator does not wait around, and that is a configurable option. The mem table is the in-memory initial write. There's also then the row cache, Bloom filters, which are a probabilistic function that says, okay, we think it might be in this SSS table, or it's definitely not. So you can get a false positive, but they don't want false negatives. Key cache, cache of the keys that have been recently accessed. Partition summaries and partition index. Partition index is your primary key index. And then there's a higher level of a summary, which is simply a collection of every 256 rows. So anyway, and it's just a sampling of the partition index to go, okay, the key is somewhere here, and then it can seek to the partition index on read. And then the SS table is the actual file that it goes to. Once it finds it in the partition index points to where it needs to go and make its read. You have tracing capability. You can turn that on as you want. And then the node tool has a CF stats, which you can then do on the cluster to find out what's going on. You can automate that so you can get an output of those so you can monitor over time. Compaction is the idea that as these SS tables get larger and larger, new ones get created and written to, and then after a while you'll have your data spread amongst multiple files, so then they bring that all back together into one, as well as doing its garbage collection at that time. And then your compaction is set at the table level. If you have one form that works better for one style of data, you can do it that way. Or other, basically the choices are you looking at a read-heavy or a write-heavy table? For hardware, CPU is the big one for write-heavy loads. You want dedicated machines, 8 processors. You can do it on one. It's just not that good of an idea. And then with your virtual machines, you want to do CPU bursting. With disk size, the size tier compaction, they say it needs to be 50% free disk space. That's not exactly true. What it is you want as much space as your largest SS table, because it's essentially making a copy of all that data, deleting what it doesn't need, and then writing it out. So you're going to wind up with less used, but you will have a duplicate of your largest SS table for a brief period of time. They do not recommend any sort of network attached storage, anything like that. You want it locally, and poor storage is usually the biggest reason that they have any performance issues. The Cassandra was originally one of the reasons they made it write specific was because of spindle drives. They wanted to try and eliminate as much as they could with that. With the advent and lack of expense now with SSD drives, that's becoming less of an apparent need. One of the big things is when we talked earlier with commit log and your SS tables, you want those split onto different drives if they're spindle. It's not as big of a deal with SSDs, but it's still not a bad idea. Network capacity is critical. They did find one of their customers had used a bunch of old 100 base T networking equipment with their machines and then wondered why they were slow. Yeah, this goes over some of the things to avoid. Select in is a very costly query in SQL. The other thing is that they have a process where it'll immediately calculate what's going on with the query and return if they think it's too much, so you have to allow filtering to go on. And that's it.
Do you have anything you can demonstrate or?
Not easily. I'm in the process. Let's see. Hold on, let me see. Okay, I'm in the process of bringing up a small 3-node cluster right now for development work for a client. This is the YAML file that you'll see with some of the things. The cluster name is ultimately what your node has. Throughout all of them, that has to match across all the nodes. Unfortunately, there's something going on with this, and they're not running right now, so that really limits what I can show you. The tokens goes into how many virtual nodes you can have, so you can limit that if you're bringing it down. They haven't really found anybody that has had performance issues going away from 150 or from 256 until they got either too small or too large. Let's see if this goes into any of the other stuff. I don't know what I can do. Okay, so here are the CF node stats for the Cassandra process that we have going on for our key space. The client currently has a 1-node cluster that we just set up for a proof of concept work. And then again, here's the described key space. If you are doing any sort of development, you'll be writing in straight CQL. There are no ORMs available for it right now. In fact, there's a large percentage of the community that doesn't want that. One interesting thing is that you'll find is that secondary indexes do not act in the same way that anything else does. They do not inhibit writes. They only allow you to do your where by a field that is not part of your primary key. So you'll see your primary key always has an index on it, and then if you have create index by name, state, whatever, that just simply allows you to use that in the where clause. If it's not there, you'll get an error back. And so a lot of people will get confused on that. The bloom filter, FP chance, just you can raise that up or down depending on if you want more performance. You can just say, look, I don't care if I get a false negative on this search, okay? Other cases, you're like, no, I have to have it, so you can change that and bring it in. Most of the data types are very similar to what you would see elsewhere. They do a time UUID, which allows you then to order by UUIDs, because time is inserted right in the middle of it. The other interesting thing I found was that they had counter, which I don't think we have any counter fields on that. It's increments by whatever value you give it, like going forward, so that you can have a table if you had a number of downloads. So you'd have just the item that you're tracking and a table that automatically upgrades or updates that, as opposed to having any sort of counting or aggregate data that you pull. Let's see. There's some of the just straightforward SQL for it. Sorry, it takes a second to go through. Yeah. Again, as long as you're not trying to do a join or a between or anything, it's just pretty much out there. The other thing I like is the collections. You have map, set, and list available to you, so that you can order those in. I don't have a wide table example that I could show you, or that would give you the idea that, say like you had a table that you wanted to do all of the albums by an artist, and then inside of those, each album would have its own column with all the attributes for that. Essentially, then you can go through, and it's a mini database is stored within the table itself, so that you can start coalescing your data into larger and larger chunks.
Pieces within that searchable?
Yes, they are. You do have to do a little bit of work, and certain of the collections present issues with that. You may have to set up your code to extract a collection and search on it. But in the individual of the columns, you can search on.
So is that what the JSON there is, or is that just?
Yes, that is. How do we set that up? Actually, I think that's just a straight string there. I don't think we did it as a particular collection at that point, because we had some additional things that we want to do. They're trying to delete inside of that section. It was easier for us to do it at the program level rather than issue a table for it.
So in kind of like a recap, and maybe we'll spawn other questions, can you kind of go back over, like, when do you think somebody would use, maybe not somebody, a particular project or application might need to use Cassandra over what they're currently using? Why would they be looking to make the move? What problem are they trying to fix?
Well, for this client, even though it's JSON in that one string, the reason we kind of set it up there is that they don't always expect it to come in JSON into that field. And so Cassandra is very good at taking from different programs and handling that if you set it up properly. So eventually what we'll do with it is the idea that our top-level UI that we're putting on it will write JSON. We can also do XML into that. Or you can set it up to have variable data types inside your tables if you wanted to. The other thing is that the volume that you're available to get on this for the hardware cost is insanely good. We had a gentleman there from Cloudwick, and they had been a Mongo house for years, already doing it. Their test cluster, they had set it up, they could get about 50,000 write or a transaction a second off of their Mongo cluster in-house. Similar cluster with Cassandra, they did 250,000. And they didn't have any Cassandra expertise. That was just kind of straight out of the box for them and running their testing. So for the volume that they got with it, the machine cost was about a third what they would have been able to, or a third of what they would spend for a standard big iron Oracle or SQL. Plus they wouldn't have that ability to take in the writes or do the storage and the seeking that they would like with that. So that was kind of their big goal with it. I know with Netflix, their thing is most of their once you log in, anything to do with the lists of movies or your preferences or the votes or anything like that is handled through Cassandra. It's very good at handling a lot of real-time feedback. They also use it partially then to monitor the rest of their network, and they collect the stats and put it in because they're very good at collecting it that way. The real-time stat collection and analysis goes on. In fact, DataStax offers Hadoop as part of their layer on top of Cassandra in their enterprise level specifically for that, for the analysis of the real-time stats. And then Intuit does a lot of their financial transactions off of Cassandra now. Because at first they were very reluctant with the idea that, look, we have to have that certain asset capability around our transactions, and after somebody dug into it a little while, they could do without it and get a lot larger performance from it. By comparison, a friend of mine who worked at McAfee was dealing with an MS SQL database. They were trying to do, I think it was about 500 million transactions a day. His servers, just one at that point, was about 1.7 million for just getting that. And then when you have to have failover, backup, staging, all the various layers of that, you're looking at almost close to $10 million for a single upgrade, a single instance of that work. And then I'm trying to think what we would be looking at. I'm going to guess probably maybe 40% of that cost if you're going to go to almost any big data, whether it's HBase, Mongo, or Cassandra. So those were definitely the ones that led over to it. The other thing is that if you anticipate growth but aren't guaranteed growth, any of the big data have that ability now to shard without necessarily causing a huge disruption. With Cassandra, I mean, their goal is that a trained person within 2 hours of realizing you have that need can add a node into the system and share the load out and go forward. And so that's another one that comes very much into that, and that's one of the appeals to some of the systems is that it's like, okay, we're starting out with a small one. If this takes off, then we're not hamstrung by it. And that's ultimately where Facebook found themselves when they invented it, is that, oh boy, we've got a scalability issue beyond belief here. So those are just some of the cases, I think, that come forward with it.
So you mentioned this thing was largely right optimized. I'm curious if you're aware of performance issues around reads, and what do they have workarounds for something like netflash you mentioned? It seems like there'd be a lot of reads there. Do they have to put something in front of that, or?
No, that, well, depends on what you're talking about. They do have certain things in front of it, but also that's where the tunability comes in at the table level, a table and the query level, is that if you need better optimization on your reads, you can easily sit back and say, okay, I'm willing to trade accuracy of the data necessarily for a faster read concept going with that. Now with Intuit, what they did is they just simply keep growing their clusters and say, okay, we're just going to add more to it because we cannot have that inaccuracy. We'll just scale as much as we can.
Right, so for read for them, they have to rebuild.
Yeah.
Step all the way back to the beginning.
When you add a node?
Well, no, when they read a record.
Mm-hmm. To a certain extent, it depends on what you're talking about. Yeah, like especially on their auditing functions or their trading functions, it can be like if they need a report back for like, okay, what's the history of this asset as it's been traded around? Yeah, it can be a large one. So they actually come up with what they call reporting tables, and so it'd be like asset by year, asset by month, asset by whatever, and add it out, and then they make those. Essentially more read heavy. The writes happen much less frequently. The writing going on the tables where they're churning, and then it's almost like an archive that it gets pushed off there to say, okay, all the activity on this is really finished up to this point that we care about, so let's write it to that table. They trade off all the write performance at that point and then go, oh, but when we run a report, good Lord, we're going to be hammering this table like mad.
Right.
So that's where they make their trade-off at that. And then one of the other things they do is they try and move everything that they can out of heap. In fact, I think memtable is the last thing that is still in heap for them, where they're bound by the Java heap size. The rest of the time they're saying, okay, we want as much RAM on the system as we can, which allows you then to scale much better with that, with just adding more RAM into the system, which is another one that they do is they'll say, you could probably get away with some more here. And that's where they go with the trade-off, like, okay, it's adding RAM to every system is going to be M, adding 5 more nodes is going to be half M. Okay, we'll just add some nodes.
Did you have any background or training in any kind of persistent storage before you began training on Cassandra?
Not really. I dealt with just general relational databases and through some of our work here. And working with some of the NAS work that I'd done at the Apollo group, but nothing specific where I'd say, oh, yeah, I was.
Just curious what the, one of the questions that I think is hard to answer because it really takes into account that kind of skill set question is, if you're looking at adding new technology stack to a project, you kind of need to know, or it's nice to know how much effort is this going to essentially be. But kind of part of answering that question is, what you kind of know already. If you have a, say, Oracle database administrator, who's done all of the system admin, all the tuning, all that kind of stuff, they have a certain mindset that's a little bit different than, say, someone who's just basically done, Java software development and never done any kind of tuning. So anyway, it's kind of an interesting question. From point A to point B, how much effort, learning curve, or additional kind of task it is.
Anecdotally, I could say from when we were meeting, one of the things that came out of it is that the guys that originally started the Facebook work were not, they were at war with the DBAs inside Facebook. And so this comes very much from a DevOps, we don't want to have to deal with DBAs mentality, which I think, though it's not obvious, I think that's kind of replicated itself, is that DBAs have, a lot of them have a hard time, especially when you start going into, okay, well, you don't have asset compliance. Well, we need that. Well, you need it in your world. We found another way. And they get that going back and forth with that sort of discussion. And then it's also then very difficult for people who are very much crutched by ORMs. And because they'll walk in and they'll be like, well, I don't write SQL now, so why do I care that CQL is very similar? It's like, well, no, because you need to write it like that. And that's the other one that you run into, is the getting kind of the opposite of what you're talking about. It's the people that have kind of totally abstracted themselves away from any sort of persistent storage their whole life and just been like, oh, my programming takes care of that. I don't worry about it. Well, they too then have that issue of, well, what do you mean I have to go in and tune my query? What do you mean I actually have to design my table structure before I even write to it? One of the things that I think that normalized data gives you is that you have that ability. It's like, okay, I've got my cities over here, my states over here, and I can do joins, and I can do all that. With this, you have to think about it up front. It's like, okay, I'm going to need this sort of table because I don't have that join. And there, just from a programming standpoint, that does break it around. I mean, this table I showed you up here, the specifications table, we now have specification attributes that go that, and then the attributes have attributes by min value, attributes by max value, attributes by the actual value of the attribute. All these tables growing out because when we were originally thinking about it, we thought about it in a relational types training. And so one part of it now is going, okay, how do we start abstracting those things out? So those are some of the things I've run into already.
So if you have these different tables, like cities by state, and you're an application and you need to create a new city, does that mean you have to basically know that you have 5 tables that this thing is a member of, and you have to do 5 writes, and you have to programmer and be conscious of making sure to do that?
For our own libraries, what we did is we took one that existed out there and extended it to create one called mirror. So that when you write once, if you write just to a new city comes into that database, it automatically knows to mirror that the concept out to cities by whatever. So with the specification attributes, we mirror out all the values that we care about on that, and then it does the right for us. But yes, you do have to account for that in your programming because you're not going to get that. There's no concept of a trigger. There's no relational addition in the database. You've got to handle it all on your own.
So if for some reason you found that you needed to write a new query to query your data in some other fashion, and in a relational land you realize that would require a new join. So in Cassandra, you would have to make a new table.
You would make a new table and populate it.
And then you have to copy from everywhere else.
Yeah, you would want to do a population script as part of your install on that. Say, okay, we've come up with, I don't know, cities by some population of the city. Well, then, yeah, it would be a new one where you're actually creating that from the beginning and then handling it from that point forward. One of the harder things to do is to change a column as it stands in the database. The primitives are just fine, but once you get beyond that, you'll suddenly run into like, oh no, you can't do that. Like, wow, son of a. So then are you looking at adding a new column and then having to delete a column later on out of your database? And those are things we didn't get into in the training I've gotten in so far, and that's where I'm being curious, is because I'm very used to the ability of like, oh shoot, I originally planned for this to only go up to now I need to be big in, so, well, what do I do?
So what do you do then?
Mm-hmm. Well, unfortunately, that one just came to my mind. Into big N, thankfully, wasn't that big of a problem, but decimal to float couldn't. because we tried to do that one. We're in the still in the development stage, so we just tear it down and rebuild it. But I would imagine what we would wind up doing is adding a column, calculating everything for that column, populating the column, and then at some later date, just deleting the one we don't need. Which unfortunately then means, well, if you have two columns, then which one is, let's say coordinates, and then coordinates _1, or coordinates by float, or, it could get ugly after a while. And so that's one I haven't tackled yet.
Another question. You mentioned at one point that it was better to have an odd number of nodes.
No, an odd number of replication factor.
Why is that?
They explained it, and I can't remember off the top of my head, other than when you're doing your that formula of plus node read plus node write consistency greater than replication factor. You do want to try and make sure it's either one above or below that. You don't want to hit it equal. But again, beyond that, I couldn't tell you. That's all for that. I'd have to look up.
Just curious.
The one slide that you had where it was things to consider to, you mentioned that it shouldn't have you shouldn't use a load balancer. Just curious if that means you should use a web application load balancer.
No, web application load balancer, yes. The load balancing concept is taken care of by the driver on the machine itself going to the database. So you don't want something in between that. You want that direct communication from the driver to what it thinks is its coordinate. But yeah, you definitely still want it above the web, or at the web layer above.
So have you used the Java interfaces? I thought I saw you were Ruby.
Yeah, no, unfortunately I've only done Ruby on this. And Java was the first driver they came up with, though. So it's probably, I would imagine it's the most mature.
A relational background before that was there. Did it take you long to adjust to thinking?
What do you mean join not support? I think they even have it as a specific error message now. Join not supported instead of just incorrect syntax because of that. But that melding concept of saying, oh, okay, I can just pull from one or the other, especially if you're used to anything where you're just like, okay, your ORM logic, you just give me these columns and these various tables. Thankfully, I'd had some SQL before, so I knew more about getting into it. The other one then is like we were talking about, designing around what your end result is. And with this client, it's a little difficult because he doesn't know where he's going with this. So, it's like later on we can, now we have enough to say, well, we could eventually have a table by every column in this main, thing if we keep up with this straight. Because he doesn't want to introduce Solr on top of this or any sort of web indexing, and we're just fighting with him going, no, there's just no way we are going to be able to write enough code to be able to do any sort of searching. Like as it stands now, we'll have to give up, type ahead search. We'll have to give up any sort of like concept. Oh, like is another one that isn't allowed in there. So that's difficult as well. As you're like, oh, and then the other tricky one is that the where not being allowed if you don't have an index on that column. Because I'm used to it, and it's like, oh yeah, I need obscure column M. And, oh, I can't do that. It's
definitely interesting.
Okay. Any other questions? Yeah, well, thanks, Scott.
No problem.
Stop screen sharing your end. And
There we go.
What screen share for you?
no screen share for me. but I can't exit. If I exit, then I'll end the broadcast. Oh. That's not good. For anybody watching remotely, the screen share button on my desktop is not working. So, I think we're going to have to end this hangout and start a new one, which is a disappointment, but I don't know if there's any other way to fix it. So, apologies for the second hangout. Wherever you found the link to this one, you should be able to find the link to the second one. All right.